In April 1990, the United States put in orbit the most powerful instrument ever devised for viewing the universe beyond our own planet. Floating 380 miles above Earth, the Hubble Space Telescope can view the heavens with none of the atmospheric distortions that plague Earth-based telescopes. From its orbital perspective, Hubble is sending astronomers hundreds of pictures that are clearer and more detailed than any seen before. Since its launch, Hubble has been joined by other orbiting telescopes, including SOHO, the Solar and Heliospheric Observatory, and TRACE, the Transition Region and Coronal Explorer. Both carry a variety of telescopes that record stunning images of the Sun. Together, these orbiting observatories are adding to the vast gallery of pictures already compiled by the many spacecraft we've launched over the years. They are sending down multitudes of images that not only expand our understanding of the universe, but inspire us with awe and wonder at their beauty. The journey you are about to take comes courtesy of America's orbiting telescopes. It will carry you from the heart of our solar system out to the most distant points in space and the most remote moments in time, to the ends and to the very beginnings of the universe. The Sun, source of all light and warmth, and genesis of life itself. Since the birth of the human race, the Sun has fascinated and intrigued us, playing central roles in myth, religion, art, and science. Now, two telescopes orbiting the Earth are showing us the Sun in ways we've never seen before. SOHO, the Solar and Heliospheric Observatory, is capturing pictures of the full solar disk, and TRACE, the Transition Region and Coronal Explorer, is sending us stunning and data-rich close-ups of the inferno that is the Sun's corona. Together, TRACE and SOHO are working to help scientists understand the Sun and how it affects the Earth in ways deeper and more detailed than ever. Not only its distance from Earth, but its utterly alien nature makes the Sun a mystery to humans. Compared to a planet like Earth, it is almost unimaginably huge, nor is it solid like the Earth. It is a fluid ball of nuclear violence that will incinerate any object coming within a few million miles. Just to observe the Sun has always required extraordinary measures, but none have been so extraordinary or so successful as those of the SOHO and TRACE instruments. While much of the Sun's energy is visible to human eyes, some is not. This visible light image, for example, reveals the Sun's surface, dappled with several dark sunspots. But above the visible surface of the Sun, the photosphere, exists the roiling cauldron of the Sun's atmosphere, the Transition Region and Corona. Ironically, though it has a powerful effect on the Earth, this sea of electromagnetic fury is invisible to human eyes, emitting light in wavelengths beyond our perception. To allow us to study the corona, SOHO and TRACE use special coated mirrors. They image the energy existing in extreme infrared, ultraviolet, and even low-energy X-ray wavelengths. Astronomers convert the data these devices capture into visible images and assign each wavelength a different color to differentiate it visually from others. The isolated wavelengths can be studied separately or combined to create a more complete picture. LASCO, one of SOHO's many telescopic instruments, captured these images in the visible light range. They dramatically display coronal mass ejections bursting from the Sun's outer atmosphere. The disk at the center of the image is a device used to shield the camera, so direct light from the Sun doesn't overwhelm the less brilliant coronal activity. Coronal mass ejections are mostly hydrogen and helium gas heated to about 1,000,000 degrees centigrade. The tremendous heat has turned the atoms of the gases into ions by stripping away their electrons. Together, the loosely floating ions and their freed electrons form a plasma that is blown away from the Sun at about 250 miles per second. This solar wind, which drags along with it huge chunks of the Sun's magnetic field, can reach the Earth in a few days. When the ions and electrons in the solar wind encounter spacecraft, they fly right through them. Any cameras recording this event see the particles as a fierce storm of electronic snow. Scientists are still studying the effects these particles may have on humans. The Sun's complex magnetic field changes profoundly in a regular 11-year cycle. At the beginning of a cycle, its internal field runs north and south. As the cycle progresses, the field is stretched east-west by the Sun's rotation. At the peak of the cycle, called the solar maximum, the magnetic field breaks through the surface, creating sunspots, heating the corona, and generating solar flares and coronal mass ejections. TRACE was launched into orbit in 1998, in time to observe the cycle as it progressed toward the solar maximum that occurred in 2001. One of the goals of TRACE was to study how the Sun's magnetic fields are related to the kind of plasma structures captured in this footage. Its observations are enhanced by its ability simultaneously to view the Sun's atmosphere, the transition region and corona, and photosphere, the surface. The movies TRACE has sent back reveal an utterly alien world. Activity during the solar max creates a monstrous panorama. Gigantic plasma arches erupt thousands of miles into space and can last an entire day. The coronal loops and arches are uncanny. Seeing them burst upwards, earthly experience suggests they would lose momentum, dissipate, scatter, and fall. But the forces controlling these eruptions are like nothing that's ever been seen on Earth. For it is not gravity, but the complex solar magnetic field that churns the coronal plasma. Material ejected with enough force will arc up and over the crest of a curved field line, then continue down the other side. But from start to finish, the plasma is confined to a tight, focused stream by the magnetic field. Less powerful eruptions will approach a peak, but in an unearthly fashion be sucked back to their origin, again tightly following lines of the magnetic field. TRACE also studies solar flares, sudden eruptions of energy on the Sun's surface. Although they last just a few minutes, solar flares can throw out sudden bursts of radiation that can affect communications and other electronics here on Earth. Changes in solar activity, including the various eruptions of solar mass and energy, certainly have an effect on human life. An exceptional dearth of solar activity between the 15th and 17th centuries created a period of cold weather so severe historians call it the Little Ice Age. Active sunspots have disabled communications satellites and knocked out power grids. They induce currents that intensify corrosion in oil and gas pipelines and put astronauts at risk from particle radiation. Globally, increased solar activity invariably increases Earth's average temperature and may affect our climate as well. The difficulty has always been to know just how and when the Sun will affect us. The SOHO and TRACE projects are adding volumes of knowledge to the field of sun science. Potentially, they will help us make great strides in understanding and contending with the powerful forces of the Sun. But we are just beginning to see the benefits of these amazing scientific tools. Time alone will tell what mysteries they eventually solve and what knowledge they bring to humanity. While the Sun is the center and source of the solar system, perhaps even more intriguing are the planets orbiting the star. The planet nearest the Sun is Mercury. Its temperature, though not the hottest of the planets, is the most variable in the solar system. It ranges from -170 to +430 degrees Celsius. Mercury bears a strong resemblance to the Earth's moon. Like the moon, its crater-covered crust has been shaped by billions of years of impacts. The planet's density indicates that its iron core probably makes up most of Mercury's mass. Venus is similar to Earth in size, density, mass, and composition, but its atmosphere is radically different. Opaque, poisonous clouds of carbon dioxide and sulfuric acid cover the surface. But in a